Hello participants, now in the subject of micro irrigation engineering, we are entering to lecture 26. In lecture 25, we discussed about different types of emission devices and how to select particular type of emission device and hydraulics of flow through drip emitters. So, emitters are water dispensing devices which are fitted with drip irrigation lateral pipeline. So, we are coming from the field emitter, then we will come to the pipes. So, pipes they are in this particular systematic order. If we start from the dripper, then it will come to the lateral, then it will come to sub main, then main. So, now in this lecture 26, we are dealing with hydraulics of drip irrigation system pipes. In this lecture, our main consideration will be how to estimate pressure loss in the pipe system, whether it is a lateral pipeline or sub main pipeline or it is a main pipeline. How to evaluate these losses. Losses could be major loss or minor loss, and how to determine the size of the pipelines, and finally how to select the size of the pump. So, let us go to the topic, details of the topic. So, hydraulics of drip irrigation pipe system. Here these pipes are made up of plastics and they are main line, sub main line and lateral pipeline. When we say main, sub main, lateral, means there is a specific arrangement and size. The drip irrigation system design must ensure the water discharging out of the dripper should be uniform. This is a very important, and this is only possible when we are making perfect accurate design. Now, maximum allowable pressure difference in the whole system, this is a limit which has been given, that allowable pressure variation should not exceed more than 20%. And in the lateral system, this pressure head loss or pressure head variation should not exceed more than 10%. Now, pressure loss takes place, or head loss, it takes place due to friction in the pipes, due to fittings. The pressure variation could be due to elevation change. So, the pressure variation in the field, it will change depending on the field situation, means it will increase or decrease depending on the way the pipeline is running. So, whether if the pipeline is running uphill, it will be, means your variation, means we need to account positive. If it is going down the hill, we have to take care about that. So, this amount are to be adjusted depending on the conditions prevailing in the field. A typical pressure head variation equation, it can be given by Pu minus Pd equal to 9.81 HL plus minus delta Z. Now, what is Pu minus Pd? It is the pressure at upstream end, and Pd is the pressure at the downstream end. When we are expressing this unit in kilopascal, one has to multiply with 9.81 in this change in this value. HL refers to the head loss in the pipeline, that is between upstream and downstream, when this is expressed in meter. Delta Z, it refers to the elevation difference. So, it can be positive when we are going up the hill, delta Z, it becomes negative when we are going down the hill. So, then there is another component, we say that HL. So, this in the previous case we are putting this here HL. So, this HL is the energy loss, and this energy loss HL is the head loss due to friction and minor losses. So, this can be given by this expression, which is that HL equal to the reduction factor in the pipeline, head loss due to friction in the pipeline plus minor losses. Major and minor losses are the two types of losses which take place in pipe flow. We will discuss in detail. So, major loss, it is the head loss due to friction, and minor loss due to fittings, and there are other accessories when we are attaching with the pipeline. The major loss, that is head loss due to friction, is given by HF. So, HF equal to this constant, then there is another component, this is also a constant multiplied by the length of the pipeline. Q refers to the discharge or flow rate in the pipeline. F refers to the reduction factor, this we will discuss, and then D refers to the diameter of the pipeline. So, these components are estimated or given, say K is a constant, that depends on the particular type of unit which we are using, or equation which we are using, for that K is to be used. So, in Darcy means when we are using Darcy-Weisbach equation, the small c is this particular component, and the m is 2 and n equal to. So, in this d 2 m plus n, when it is given, so this m is 2 and n is 1, and here also q is in q to the power m, this will be m square. Similarly, for Hagen-Williams equation, we will be using these constants if we go for Hagen-Williams equation to estimate the head loss due to friction. Now, if we are using Hagen-Williams equation, that particular equation is brought in this form, where means head loss due to friction in 100 meter pipeline can be given by this expression, where K is unit constant and Q by C, that is Q is the discharge through the pipeline in liter per second, C is a constant that depends on the particular type of pipe material, and then of course, this means normally the value of this C it varies from 120 to 150. So, 120 to 150 means what is the type of material. If it is a PVC pipe, then the value of C is different. Of course, that will depend upon what is the diameter of pipeline which we are using. If it is a high density polyethylene pipeline, then value of C is different. Also, that will depend upon what is the diameter of pipeline which we are choosing. So, there is a range of, I am just giving you, that is 100 to 150 is the range for C. D is the diameter of pipeline, which is given in millimeter, and F is the reduction factor. Now, this reduction factor, it is to be used when we have got number of devices, means emission devices or outlets which are attached with the lateral pipeline. Now, how these outlets are attached with the pipeline? So, when distance from the pipeline to the first outlet is equal to the outlet spacing, means all the emitters of the first emitter to the last emitter, they are equally spaced. So, first emitter will be equally placed as other emitters are from the when we are attaching with the means in the lateral pipeline. So, in the lateral pipeline the drippers are attached. So, it is this expression will be used m. Here what you are seeing, that m is the exponent. If you are using Hazen-Williams equation, the value of m is different. In case of Darcy-Weisbach equation, the value of m equal to 2, n is the number of outlets, that is your number of emitters. And when the distance of the first outlet is half of the outlet spacing, let us put it that if they say we are keeping the spacing between the outlet, means drippers are 2 meter apart, let us say. So, first emitter which will be kept in the lateral pipeline, when we are attaching with the sub main, it will be at 1 meter, and then all other remaining emitters will be at 2 meter spacing. So, this is the arrangement. Normally, this equation is used in case of sprinkler irrigation system, means when we are using the overhead sprinkler system, this equation has got more relevant. In case of dripper, because number of outlets are too many. So, effect on the reduction factor by keeping first emitter does not give much difference in the value, but yes, it will give more value, because there in case of sprinkler irrigation system spacing is quite large. It could be 12 meter, it could be 18 meter like this. So, there we take care. Now, the other part of the flow through the head loss due to friction to estimate by Darcy-Weisbach equation. So, this is a popularly known equation, HF equal to FL V square by 2 dg, and these are the values. So, here means your HF is the head loss due to friction, F is the Darcy-Weisbach friction factor, and that can be obtained by from the Moody diagram. G the acceleration due to gravity, and L is the pipe length, V is the flow velocity. So, these are all the things which are there. Now, Moody diagram is, this is the diagram, and you can see here in the Moody diagram, this is a plotted between friction factor and Reynolds number. So, Reynolds number already I have explained you, it is the ratio of the inertial force to the viscous force, which can be given by rho V d by mu. So, V the velocity of flow in the pipeline, what is the diameter of pipeline, and rho is the density of density of fluid, that is a water, here we are using, and mu is the dynamic viscosity. So, you can see for the laminar flow range, this is the so the value of F is for the laminar flow range, it is in this range, it will be in this range, whereas in case of turbulent flow range, this the value means here this particular diagram will be used, and for transitional flow range these type of this will be used. So, here the friction factor is estimated by taking a particular type of the pipe material which has got some certain the resistance, that is the roughness value. So, this epsilon is the roughness value for the different types of pipe material, and then the relative pipe roughness is given, that is your roughness, this is your epsilon, and then relative roughness is given by the epsilon by d. So, we will be choosing the appropriate value of epsilon by d, and then also we will choose the we will by estimate the Reynolds number and then select obtain the value of friction factor. Minor loss is the another component, means it is estimated, it can be estimated or obtained from the standard table. Yes, table is provided or one has to estimate, but estimation becomes difficult because those head loss coefficient are to be also known to us. So, normally tables are used. So, minor loss, where from the minor loss it is coming, it is from the bends, then it comes from the several fittings, and these minor head losses are expressed equivalent to the length factor, means it is not only the 30 particular value. So, what is the length it is there, means it has to be brought in terms of meter, means equivalent length factor. So, that a to the virtual length of the straight pipeline, means maybe say from the barb we are telling. So, barb it has got a specific it is bringing down the factor. So, barb coefficient that is multiplied and it is expressed in terms of the equivalent length value. So, this is a table. Here this table practically it gives the value of different the minor loss coefficient. So, head loss due to different fittings can be given by KL into V square by 2G, and then the values of KL are to be given depending on the type of fittings which we have given. So, it could be elbow like this, it could be 180 degree bend, it could be tees, it could be union. So, in field situation when we are using we will come across these types of fittings. Maybe we are required to reduce the size of the pipeline, we are required to increase the size of the pipelines, means reducer, enlarger, such type of the attachments joints are needed, and it causes the loss in the head loss, and that is to be calculated, so that we can accurately get the value of head loss due to friction. Now, design of lateral pipeline are hydraulic link between main pipeline or sub main line and the emitters. So, emission devices can be connected directly to the lateral line, and lateral will have hydraulic fittings, tees, unions. Just now I told you that this will cause the fittings, and it will have the loss to connect to the main, sub main or main line. So, Darcy-Weisbach equation is used to compute the head loss due to friction. This gives the accurate estimate, region being the here it is taking care of the flow condition, flow regime, means flow could be at the lower velocity or flow is at higher velocity. So, turbulent flow, laminar flow, this takes care, and accordingly the value of F is used, whereas in Hagen-Williams equation that is only when the flow is in turbulent condition. So, Reynolds number is estimated by inertial force, that is rho V d by mu, and K is the unit constant. Referring to the Modi diagram, you have seen that for laminar flow the value of F can be estimated by using this expression, whereas in case of turbulent flow the value of F can be estimated by using the this equation, and when the flow becomes fully turbulent, so F can be computed by using this expression. Now, F appears in the left side as well as right hand side of this expression. So, here trial and error means we have to make a repetitive computation in order to get the correct estimate of the value of F. Design of sub-main pipeline in the hydraulics is similar to that of lateral pipeline hydraulics, and sub-main line is designed to allow the approximately same energy loss as compared to the lateral line for several laterals and submain line. So, naturally the amount of water which is being delivered by the submain pipeline, it will be the number of lateral pipeline which will be attached with the submain pipeline, that is the, and then how much is the pressure loss it takes place. So, it will depend upon the how many number of submain pipelines they are attached. It is Keller and Carmeli, the two investigators, they have recommended that lateral energy loss should be 55% and submain energy loss should be 45% of the total allowable energy loss. So, this is the proportion that can be taken care while we are estimating. We should see that the part of the energy which goes from the lateral pipeline and submain pipeline, what is the percentage it comes. Submain design depends on the location of the flow or pressure regulation. Energy loss in the submain is directly related to the length of submain line. So, energy loss cannot exceed the allowable limit without lowering the uniformity. This is the another part, that is, if at all we are taking care about the energy loss. So, at that time we have to see that uniformity should not be compromised. The submain hydraulics characteristic can be computed by assuming the laterals are analogous to the emitters on lateral lines. Yes, this is correct, that yes, it is similar to the, as the laterals are delivering water to the emitters. So, here submain is delivering water to the laterals. So, hydraulic characteristics of submain and main pipes are usually taken as hydraulically smooth pipeline, because they are made up of PVC. Normally these are used. So, PVC or HDP, this is a plastic material. So, smooth, they are smooth pipeline, and it can be assumed in the same way. The energy loss in the submain pipe can be computed with methods similar to that which is used in the case of lateral case. Now, main pipeline, the flow or pressure control or adjustment values are provided at the submain inlet. Therefore, energy loss in the main pipeline should not affect the system uniformity. The main pipe size is based on the economic comparison of power cost and pipe cost. Yes, this is another important part, that we need to see that how much is the energy being consumed. If you are going for too low size pipeline, we may reduce the cost of the system, but the recurring cost, operational cost will increase because of the lower pipeline. So, head loss may be lower. So, that is one trade off between this selecting the energy consideration, power consideration, and the cost of the system. Main pipeline should be selected so as to minimize the sum of the power cost and capital cost over the lifetime of the pipeline. So, in case of lateral pipeline, submain pipeline and main pipeline, it is standard practice to start design by considering the minimum available pipe diameter till it satisfies the allowable head loss condition. So, what we are seeing here, that the means when we are deciding the main pipeline sizes, when we are deciding the submain pipeline size, when we are deciding the lateral pipeline size, we need to see what is our layout in the field, and layout will depend upon our field condition, which I discussed in previous lectures. So, we need to take care while we are deciding. So, layout should be taken, then hydraulics should be taken care. Water supply in manifold. The water supply manifold consists of a pump, valves, chemical injectors, pressure regulator, filters, water meter, vacuum breaker, automatic controllers, etc. So, pump operating range is selected based on the number of operating subunits and their flow rate and the total system head. It is not always possible to supply water to all the subunits. So, we can reduce the size of the pump and seeing that how many number of hours electricity is available or how many hours the pump can be operated. So, means the size of the pump can be selected accordingly. So, system flow rate is the sum of the flow rate in each concurrently operating subunit, and then system head is the sum of lateral inlet pressure, head, elevation difference from the pump to the highest lateral inlet, energy losses between pump and lateral to the to include sub main frictional loss, valve loss, main line loss. So, this is a important, means we will consider what is the flow rate, we will consider the total head considering these points. The filter loss will represent energy losses resulting from partially clogged filters and screens. Usually these energy loss will have fixed range between 30 to 100 kilopascal depending on the type of filter which we use. So, we will discuss about these points, and of course, this loss will also depend upon the particular type of filter when we are using it in detail. Now, when we want to work out the horsepower requirement of the pump. So, horsepower requirement of the pump is given by total pumping head multiplied by the discharge from the main divided by 75 into the pump efficiency and then the motor efficiency. So, this particular ratio, this particular computation will give the horsepower requirement of the pump. So, this discharge coming out of the pump, it is expressed in liter per second. This is the total this is the total head, and this total head is sum of the head means required at the means your head loss due to friction in the main pipeline, head loss due to friction in the sub main pipeline, head loss due to friction in the main pipeline, and then the losses from the accessories. This also includes the other component, the total head, and then other component. What I am telling that this is your operating pressure requirement for the dripper. So, normally for the drip, the 10 meter water column 1 kg per square centimeter pressure is enough to operate the drippers, and Hs is the total static head, that is the the suction head plus delivery head. So, that already I have discussed when I was telling you about the selection of pumps. So, this H is computed when Q is known to us, then we can, and also the efficiency of the pump as well as the motor, it is used to compute the horsepower requirement of the pump. You may refer these books, and then in this particular lecture we let us summarize the part that we discussed about the losses taking place from the pipeline. These losses could be the major loss or minor loss, and then We also discussed about the hydraulics of flow through lateral pipeline, sub-main pipeline, main pipeline, and also we discussed about the horsepower determination of the pump. Now, in forthcoming lecture, we will work out some numerical problem dealing with the design of drip irrigation system. Thank you very much.